Hello, welcome to Solve Papers channel. I'm Godfrey. In this video, I'm working out how to Chemist paper 5. This is a planning, analysis, and evaluation paper. May, June 2019. It is variant 5.2. This paper is 1 hour 15 minutes. Of course, no additional materials are required, but you need your pen, your pencil, your ruler, in case you need to draw any diagrams or graphs. Well, before we start, if you have not already subscribed to my channel, guys, please click the subscribe button and hit the bell icon. In this way, you'll be notified every time I upload a new video. I also encourage you to like my video, and if you find it useful, you can share it with your friends. That will be quite a blessing. Very well. Let's get started. A student is provided with samples of 6 metal carbonate ores, known to be ores of metals, barium, calcium, copper, iron, lead, and zinc. All the ores contain carbonate ions, and some might also contain hydroxide ions. Each ore sample is ground up and a measured mass of the ore is reacted with excess hydrochloric acid. The carbon dioxide produced by the reaction is collected over water. The volume of the gas is recorded. Each ore is tested 3 times. Name the independent variable. Name the independent variable between the carbonates, dilute hydrochloric acid, and the carbon dioxide that is obtained. Of course, there is going to be a salt that is going to be obtained as well, especially when you react a carbonate plus HCl. What you get is a chloride salt plus carbon dioxide plus some water. So among these, the independent is the variable. The independent variable is the carbonate. It is the one which will determine how much carbon dioxide is going to be obtained. So the ore of carbonates, the ore of the carbonates is the independent variable. Name the dependent variable. Dependent variable is carbon dioxide because it will depend on the mass of the ore that is reacted with excess hydrochloric acid. So the volume of carbon dioxide produced, because the carbon dioxide produced depends on the amount of ore used, because it depends on amount of ore used. Part 2, apart from mass of ore, state a variable that should be controlled. We know carbonates, when they are heated, they decompose. Metal carbonates, when they decompose to give an oxide and carbon dioxide. So you need to control temperature. Temperature should be controlled. The student plans to collect carbon dioxide produced over water. Draw a label diagram of the apparatus. Draw a labeled diagram of the apparatus that could be used to do these experiments. The apparatus should show how the accurate recording of carbon dioxide produced. How should allow the apparatus should allow the accurate recording of CO2 produced. Of course, you need a conical flask with a sprout. You need a conical flask. So let me draw this. conical flask. Of course, you need to have the oil in a small test tube. Right there. Then you have your acid there. That is the oil there. You have your stopper right there. You have your trough with water. You have the trough. You have your delivery tube here. Should come to, let me draw it here. Let me draw the trough not very far away. You can have a beehive. Then you can have a measuring cylinder on top of the beehive. You have your water there. So this is measuring cylinder. This is water trough. Of course, this should be sealed. This is a sealing so that no gas escapes. You need to have your clamp here. You can place your clamp right there. This is your clamp to hold the conical flask. This is a conical flask. This is the oil in there. This is the oil. This is the dilute HCl. Yeah, I think that is a good diagram. So part B, state one weakness in the procedure of collecting carbon dioxide of water. Suggest a change in the apparatus that could be used to avoid this problem. Weakness is that carbon dioxide is soluble in water. That's why when it dissolves, you get carbonic acid. So CO2 is soluble in water. Soluble in water, so some of it will dissolve, so we will not get all the carbon dioxide that is produced here. So the volume that you get here will be less than what has been produced. Some of it will have dissolved in the solution in water. The change in apparatus, you rather use what we call gas seerage. Use gas seerage instead. A seerage will also help you record or measure the amount of the volume of carbon dioxide that is being produced. So that is a good substitute there. Part C, 3 experiments for each of the 6 oils are done and the final gas volume are recorded in the table. All 16 experiments use exactly the same mass of ore. You can see barium all the way to zinc metals, and the name of the ore right here. Experiment 1, 2, 3, a volume of carbon dioxide collected in centimeters cubed, and the average right there. The student uses the results to obtain an average volume of carbon dioxide, produced for each ore and records it in the table. Suggests another reason why each ore is tested 3 times. Of course, every experiment should be repeated, and for the this is for the purpose of improving the reliability of your results. So this is to improve. The reason why you're doing 3 times is to improve the reliability of the results, such that if you have made an error in one result, that can be spotted easily when you compare it to the other results of the same experiment when you repeat it. Part 2. The student made an error in processing the data to obtain the average volume of carbon produced for one of the ores. Processing the data, not obtaining the data from the measurement. State the error made by the student and calculate the corrected value. The error is that the student used anomalous result. The student has used an anomalous result. When you check, you should check all the results. Check across all values. In all the values. Of course, you'll notice that the error is in the first carbonate, which is by the name witherite, right here. This witherite here, the processing of this data was there was an error there. You notice that the calculated average is 69, and therefore if you multiply 69 times 3, this will give you 207. But when you add 67, which is the data here, 67, 70, and that is 67 plus 70 plus 69. When you add all those, 67 plus 70 plus 69, what you get is 206. Therefore, 206, when you divide by 3, you get 68.6, and this is supposed to be 69 right there. Part D. A second student suggested that the percentage of carbonate ion could be obtained by titrating the ground up all samples with hydrochloric acid. Explain why titration would not be a suitable method to determine the percentage of carbonate ions in some of these ores. You remember, in some of these ores, it was said that they contained, some of these ores, it is said that they contained, let me point out that to you, excess contains, and some contains the hydroxide oils. So if some of them, all the oils contains carbonate ions, and some might also contain hydroxide. So if you react an acid with hydroxide ions, then this reaction is going to happen to give you water. So that might not be a good idea to titrate the oils with an acid. That is explain why the titration will not be a suitable method, because the acid, we are explaining, the acid will react with the hydroxide as well as the carbonates. So the only good way is to get the acid react with the hydrochloric acid, and then you get the carbon dioxide that is produced. Okay. Rhodochrosite is the carbonate ore of manganese and does not contain hydroxide ions. 2 grams of rhodochrosite produced 148 centimeters cubed of carbon dioxide under room conditions in its reaction with excess hydrochloric acid. Excess to make sure that all the carbonates reacts. Calculate the percentage of manganese carbonate in rhodochrosite. Give your answer to 3SF. The molar volume of a gas is 24 dm cubed under room condition. So we need to calculate the percentage of this in chrosite. We need now to see how much moles of carbon dioxide were produced, and you can see that every 1 mole of carbon dioxide, 1 mole of carbon dioxide was produced to 1 mole of manganese carbonate. So 1 to 1. So the number of moles of carbon dioxide produced would be the same number of moles of manganese carbonate. So moles of carbon dioxide, moles of CO2 is you're given here the molar gas. So 1 mole of a gas is 24 centimeters cubed, 24,000 centimeters cubed. You change the dm cubed into centimeters cubed, right? And then you ask yourself, then 148 centimeters cubed is how many moles, and cross multiply. So you'll get 148 divided by 24, this is centimeters cubed, this will cancel, and what you'll get is 0.006167 moles of carbon dioxide produced. And of course, this number of moles are equivalent to the number of moles of manganese carbonate. So we get the MR of manganese carbonate. MR of manganese carbonate is 114.9. You add 54.9 plus 12 plus 16 times 3, you get this. Therefore, that's the moles. So the mass of manganese carbonate produced is mass is equals to moles times MR. So 0.006167 times 114.9, and this will give us a mass of 0.70855. We need the percentage, so we are going to out of 2 grams of this all, 0.7855 grams was magnesium carbonate. So what percentage is that? So to get the percentage of manganese carbonate, it is this mass 0.70855 divided by 2 grams times 100, and this will give us 35.4%. Very well. A teacher suggested that the mass change from the thermal decomposition, of a ground up sample of rhodochrosite could be used to determine the percentage of carbonate in the sample. The teacher told the student to strongly heat a ground up sample of the ore in a crucible. State the measurements the student should make to determine the percentage manganese carbonate in the sample of rhodochrosite. Of course, you need to measure the mass of the crucible. He's heating the crucible, so measure mass of empty crucible. Then you put your ore there, so you get mass of crucible, and the ore before you start heating. Then after you have heated strongly, get the mass. To get the difference of the mass, get the mass of crucible and the ore residue. After, of course, the ore has undergone thermal decomposition after heating. Then, of course, you can get the difference right there. So if this is M1, this is M2, this is M3, then the change in mass will be equal to mass of crucible before heating minus the mass of the crucible after heating. It'll be basically M2 minus M3. That can give you the change in mass of the ore. You can also remove the M1 from M2 and M1 from M3, and then you go ahead and find the difference again. It will give you the same thing. Explain how the students can ensure the results in part part 2 are as accurate as possible. You should make sure that you heat the contents of the crucible, heat the contents of the crucible to a constant mass. This is to make sure that all the carbonates has undergone thermal decomposition and none of the carbon is remaining undecomposed. You can get all solved Chem paper 5 from 2016 up to 2019 from this site, solvedpapers.co.uk. If you need all paper 5s, chemist L2 solved, you can head to this site. The site I'm talking about is this site here. This is solvedpapers.co.uk. You can have a look at it. You need to go to A-level chemist. The paper you're dealing with right now is 2019 June. You can go here, and of course you come to this point here. Come to this point. You find these papers here. The ones that I'm talking about is this paper. I'm doing June 2019, paper 2. This is the paper we are dealing with right now. You can download this, and if you need all the others that are be solved, you can click here. Click here to get Chem paper 5 solved in a zip folder. Of course, when you click there, you'll come here. They are all here. This is paper 5. You can click here. Get chemist and physics. A2 past paper. Papers 5 solved. You can get for November. You can get for June 2019, 2018, all the way to 2016 chemist is solved right there. So you can get all these papers and practice. Practice is key. You can request your parents to help you with this, and just click here. It's only 10 pounds. I'm sure there is something that you can be able to do with assistance with your parents. And then practice working out these questions. Paper 5 is a little bit taxing. You need to practice a lot and get it right so that you get your A star in chemist CIE. I also do online classes. I also do online tuitions. If you need my help, I'll be glad to help. You can find me in this site here, spacademy.co.uk. I'll be very glad to help. The site I'm referring to is this one here. This is SP Academy. You can find time and explore our site. We do chemistry, mathematics, physics, biology, and ICT. Can explore the site. What I need you to do is to check our student guide. You can click here or here to get a guide, a step-by-step guide on how our site works. You may also watch this video to get familiar with our online live classes. Once you make up your mind you need my help, then you can click here to register. I need you to register and create your own account. Of course, we'll send you an email to activate your account, so give us the correct email. Once your account is activated, you may sign in, and then in your dashboard you can click here to find a tutor. Then you can request for assistance. We'll be glad to help you get your A grade. That will open university doors for you. Great. Let's proceed to question number 2. Question number 2. An investigation is done to find the percentage of copper in a brass nail. Percentage of copper in a brass nail. The brass nail is dissolved in concentrated nitric acid, and the resulting solution is diluted with distilled water. Brass is an alloy of copper and I think some other metal there. Copper ions are formed in this reaction. When brass dissolves in concentrated nitric acid, then we have copper ions right there. Use the electrode potentials to write a balanced ionic equation for the reaction between copper in the brass nail and the concentrated nitric acid. Balanced ionic equation for the reaction between copper and concentrated nitric acid. All right, that's what you need to write. So you can see here these are reducing electrodes right here. So one of them has to be an oxidizing electrode, and since it is copper that is reacting to give us this ion, then you change this equation. And of course, the equation that we'll use is this and this, because we have copper, because it is copper and concentrated nitric acid. We have copper here, and we have copper ions, and we have nitrates here in nitric acid and nitrogen dioxide that is produced. So we will not use this because here we have copper ions, copper 2 ions and copper 1 ions. That is not what is in the brass. What we have in brass is copper atoms, and here we have the acid hydrogen here. We don't need this, so we only need these two equations. So in this equation, you change it and write it this way: copper will give us the reversible reaction, give us copper ions, give us copper 2 ions, aqueous, because that is what we are getting here, plus 2 electrons. Okay, so we'll use that equation, and then we also use this other equation. So we will basically be adding, let me write this equation here, be adding copper solid plus, sorry, not plus, copper give us copper 2 ions plus 2 electrons. But you can see this is 1 electron, this is 2 electron. So we need to multiply the whole of this equation by 2 to get 2 electrons, so that the 2 electrons will now cancel if there are 2 electrons. So everything here becomes 2, this becomes 4, this is 2, and this is 2. Then you add the 2 equations. We add the 2 equations. So we will have copper solid plus nitrate ion aqueous. This is 2 plus 4 hydrogen ions aqueous, and this should give us copper ions aqueous plus 2 nitrate, 2 nitrogen dioxide plus 2 molecules of water. Yeah, I think that is the equation that we need to write. Use the electrode to write a balanced equation between copper and nitric acid. There you are. Part B. A balance accurate to 2 decimal places was used to weigh a small beaker, and the mass of the beaker recorded. The brass nail was placed in the beaker, and the mass increased by this much, 3.76 grams. Calculate the percentage error in measuring the mass of this nail. Of course, you can see it's measured to 0.01. So the error here is equals to 0.01. Of course, we always divide this one to get 0.005. So per measurement, right? Per measurement. So we have the initial and the final. So initial and final. That's why we are getting this error. Would be equal to 0.005 times 2. And therefore, we are getting 0.005 times 2 divided by this mass, 3.76 times 100. This should give us the percentage error of 0.27%. So the percentage error is 0.27%. C. 50 centimeters cubed of concentrated acid was added to the nail in the beaker, concentrated nitric acid. When the reaction finished and the nail had dissolved, the reaction was completely transferred to a 250 centimeter cube volumetric flask along with the washings. The solution was made up to the mark with distilled water, right? 250. Concentrated nitric acid is corrosive. State one precaution related to this hazard that must be taken when using concentrated nitric acid. You should make sure the acid does not come in contact with your skin, because it's going to really corrode you. So the only way to make that does not happen, you need to wear protective gloves. While you will be handling the acid. Of course, when the acid comes into contact with the gloves, you'll still be safe. Part D. A calorimeter can be used to determine concentrations of metal ions in solution. When a calorimeter, of course, uses light. When light passes through a solution of metal ions, some of the light may be absorbed. The quantity of light absorbed is called the absorbance and is measured by a calorimeter. The absence of solution of known concentration of copper 2 ions can be used to determine the unknown concentration of copper 2 ions. Solution of copper 2 nitrate of concentration 0.8 moles per liter is required for this investigation. Calculate the mass of copper nitrate needed to prepare 100 centimeters cubed of 0.8 moles per liter solution. Give the answer to 3SF, given the relative atomic masses of copper, nitrogen, and oxygen right there. So we can find the relative molecular mass of copper nitrate. And once you calculate correctly, you get it is 187.5. Then we can get the number of moles that are in 0.8 that are in 100 centimeters cubed of 0.08. Of course, we know that 0.8 moles are in 1000 centimeters cubed. Then in 100 centimeters cubed will be how much moles? Of course, so the moles will be equal to 0.8 times 100 upon 1000, and this will be equal to 0.08 moles. We need to calculate the mass of copper in that. So mass of copper, mass is equals to moles times mr. So the moles we have gotten here is 0.08 times mr, which is 187.5. And when you do correctly, you'll get 15.0 grams. This is the mass of copper 2 nitrate. Mass of copper 2 nitrate in 100 centimeters cubed of 0.8 moles per liter. So this is 15. Okay, volumes of 0.8 moles per dm cube copper 2 nitrate are diluted with distilled water to prepare a series of 10 solutions of different concentration of copper 2 ions. The volume needed for each of the solution is only 20 centimeters cubed. The absorbance of each solution is recorded in a calorimeter at a wavelength of light of 613 nanometers and recorded in the table. Complete the table to show the volumes of 0.8 moles per dm cube copper 2 nitrate and distilled water needed to prepare each solution. Give all volumes to 2 decimal places. Alright, 2 decimal places. So the initial volume, solution 1 was basically water. These can go for 1.1, and this will now become 19. Of course, can go for 2 or even 3. Can go for 3. This will be 17. We can go for this is 4. This will be 16. All of them should be in 2 decimal places. Okay, can go for 5.5, 5.50. This will be 14.5, 7.50. This will be 12.50. 9 will give us 11 amounts of water required. 10.50 will require this amount of water. 12.00 will require this amount of water. This will require 5 of water. So there we are. Okay, nitrate, give volume of 2. Okay. You're getting these volumes here based on the concentrations of copper oxide. So you need to calculate that. And the total volume should always be 20. Okay, should always be 20 right there. Complete this table because you're taught to complete the table. Complete the table to show the volumes of that of copper nitrate and distilled water. So you need to calculate this. Volumes of copper nitrate. Of course, I'll show you 2, then you can do the rest. Let's do for the first column here. We are given a concentration of copper 2 aqueous moles per liter. So we have 0.04 moles in 1000 centimeters cubed. We want to find what will be the number of moles of copper 2 ions in 20 centimeters cubed. Of course, you can cross multiply. You say 0.04 times 20 over 1000. This will give you 0.0008 moles. And we know we are given here that we want to find what volume of copper nitrate we need. So we are told here we have 0.8 moles of copper nitrate, 0.8 moles per liter. So we have this in a liter. So we will ask ourselves then what volume will 0.0008 moles be in. Then you cross multiply, say 0.0008 times 1000 divided by 0.8. When you calculate nicely, you'll find that the volume is 1 centimeter cubed. This volume here. So you'll need 1 centimeter cubed of copper nitrate to get 0.04 moles per liter of copper 2 ions. And therefore, since you have 1 centimeter cubed of this, you need to add 19 centimeters cubed of distilled water to get a volume of 20. That is one. Let's do the second one, this one, to know what volume of water what volume of copper nitrate we require. So you say here you are given 0.12 moles of copper nitrate in a liter. So we have that in 1,000 centimeters cubed. Then you ask yourself, then in 20 centimeters cubed, what will be the number of moles? Then you multiply this times 20 or divide by 1,000, and what you get is 0.0024 moles. And we know that we have these 0.8 moles per liter of copper nitrate. So we have 0.8 moles in 1,000 centimeters cubed. So this number of moles will be found in what volume? So 0.0024 moles will be in what volume? So we cross multiply 0.0024 times 1,000 divided by 0.8, and when you work out this, you'll find this is going to be equal to 3 centimeters cubed, what we have here. And since the copper nitrate is 3 centimeters cubed, then you'll need to add 17 centimeters cubed of distilled water to get 20. Therefore, you work the rest in that way to be able to get this number of this volume of the copper nitrate that is required. Once you get the volume of copper nitrate that is required, you only now subtract 20 minus this volume to get the volume of water, distilled water that needs to be added. And that's it, how you get these volumes. Very well. Part 3. Name a suitable piece of apparatus for accurate measuring the volumes you have calculated. Suitable apparatus is a burette. I'll go for burette. We have, of course, measuring cylinder. We also have a pipette, but the most suitable here is burette, because burette will give you into 2 decimal places volume. Part E1, the plot produced by comparing the absorbance of each solution with its concentration is referred to as a calibration graph. Plot a calibration graph of absorbance, y-axis, against concentration of copper 2 ions, aqueous, x-axis. Use a cross to plot each data point. Draw line of best fit. Draw line of best fit. So we are going to plot absorbance against the concentration of copper ions. This is the data that you're supposed to be plotting. The absorbance against the concentration. This is going to be on the y-axis, and this is going to be on the x-axis. Okay, so let's do the plotting. Let's do the plotting. So the first is absorbance is 0, 0, and copper is also 0, 0. So we are going to use crosses. So there you are. That is the first point. The second point is absorbance is 1, 2, and copper concentration is 0.4. So 0.4, this is 0.1. So each one of these is 0.01. You can of course say this is 10 divisions. 10 divisions, of course it's going to be 0.1 divided by 10 divisions. This is going to give 0.01. So each one of these division is 0.01. So then for us to get 0.4, you need 4. 1, 2, 3, 4. 0.4 is there. And the corresponding absorbance is 0.12. So we have here we have 0.2, and we have 10 small boxes, so this will give us 0.02. So each one of these is 0.02. So 0.12 divided by 0.02, what does this one give us? This is 12 divided by 2, this is 6. So we have we need 6. So 5, 6. So that is the next point. The other point is 0.36. Absorbance is 0.36. 0.3 is there, so 6 is there. 0.36 is right there. Sorry, I'm looking at a different one. So it is 1.2. 1.2 is there for absorbance, and then that corresponds to 0.36. So 0.36 0.36 is 0.36 divided by 0.02. This will give us 36 divided by 2, which is 18. So this is 10, and 18 is here. So right there. Okay, so the next is 0.16. 0.16 is there. 0.16 is right there. Corresponds to 0.48. 0.48. This is 0.5. So 0.48 is here. No, that is 0.6. 0.48 is there. Okay. 0.22 right there. This corresponds to 0.66. This is 0.2. Maybe sure of that. 0.2 divided by 10. This gives us 0.02. Yeah, so 0.02. So 0.06 divided by 0.02. This is 3. So 3 from there is there. 0.66. 0.3 is here against 0.89. 89 is somewhere here in between there, because this is 0.9 here. This is 0.9. Okay. The next is 0.36. 0.36 is there. This corresponds to 1.6. 1.6. 1.6 is here. 1, 2, 3. 1.6 is here. 1.06. Not 1.6. 0.6 is right there. Okay. 0.42. 0.42 is right here. Then 1.25. 1.25. 1.25 is here. Now this is 1.3. So 1.25 is in between here. 1, 2, 2.5 is in between there. Very good. And then we have 0.48. 0.48 is here. Corresponds to 1.41. 1.41. So 1.41 is 0.8 is there. So 0.8. So 1.41. So 1.41 is here. Is right there. Let me draw a clean one. Yes, right here, in between there. Okay, then we have the last one is 0.6. 0.6 is there. Again, it's 1.76. 1.76. This is 1.7 here. And 6 is right here. Good. So we need to draw a line of best fit. Draw a line of best fit. So let me zoom out so that I may draw the line. Let's zoom out again. And there, so I can now draw the line of best fit. And that is good. So that's what we needed to draw, line of best fit, and that is good. Part 2, state the relationship between concentration of copper ions and absorbance. You can see the graph is a straight line through the origin. The graph is a straight line through the origins. That indicates direct proportionality. So the relationship of copper concentrations and absorbance is directly proportional. Increase of one increases results to the increase of the other. Directly proportional. The absorbance of the solution prepared in C from the brass nail was found to be 0.56. Use your calibration graph to find the concentration of copper ions in this solution. Calibration of copper ions in this solution. So we go to our graph. We go to our graph here. We find absorbance of 0.56. This is 0.5 here. 0.56 is right here. So you come to the graph, and then you come down. Right there. So 0.19 is the answer. 0.19. This is 0.19. So an absorbance of 0.56 is when the concentration of copper is 0.19. So concentration of copper here is 0.19 moles per liter. Okay. Part 2. Use your answer to F1, which is 0.19, and the further information in B and C to calculate the percentage of copper by mass in the brass nail. Give your answer to 3SF. If you were unable to obtain an answer of F1, you may use the value of 0.22. This is not the accurate value. This is not the correct value. So we have from 2C, volume used was 250 centimeters cubed. And from 2B, mass was 3.76 grams. So if you can refer that. Then, of course, to get the number of moles in 250, this is in a liter, moles of copper ions in a liter. So moles of copper in 250, moles of copper in 250 will be equal to 0.19, this value here, 0.19 times 250 over 1000. That is the number of moles of copper, which is copper ions, which is 0.0475 moles of copper to ions. So the mass, you're supposed to calculate the percentage of copper by mass. So the mass is moles times MR. Of course, MR of copper is 63. So can just give it here. That is relative atomic mass of copper is 63.5 given here. Okay, so mass is equals to the number of moles of copper, 0.0475 times the R, which is 63.5, and what you get is 3.01625 grams. Okay, and therefore the percentage of copper by mass, percentage of copper by mass is equals this 3.01625 divided by this 3.76 times 100, and what you get here is mass. What you get here is 80.2%. 8.2%. Yeah. Okay, that's it, guys, for this paper. You can see the way we've worked it out. Of course, get more Chem Paper 5 solved in this site here, solved papers.co.uk. You can get all chemist paper 5s, 5.1, 5.2, 5.3, all solved since 2016 to 2019. If you need my help, I said I do online tuitions. You can get in touch with me from this site. Alright, I'll see you in my next video, guys. Cheers.